Hi, everyone. My name is Matt Carbone, and I'm going to talk to you today about a project that has dominated the last year or so of my graduate studies at Columbia, the topic of which is a numerically exact solver for electron-phonon lattice models in the Polaron limit. So without further delay, I hope you enjoy the talk. All right. So I'm going to start with a quick outline of what I'm going to talk about today. And first, of course, is what we are actually doing here. The target of interest is called the single particle response of a system, otherwise known as a Green's function. And this response function characterizes what happens when you inject an electron into an otherwise empty lattice, in this case, or a system more generally. And in our method, we're going to propose an approach that is methodologically unconstrained or systematically exact. And what we mean by this is that if you had an unlimited number of computer resources, you could solve for the exact Green's function, a quantity that is otherwise out of reach, because mainly the systems are usually too complicated to solve for this quantity exactly. So why are we doing this? The first is theorist's curiosity. There are many model systems of interest that are unsolved that would yield significant physical insight if they were, insight that perhaps could inform real material design. And there are actually real materials that you can map onto these model systems that I'll discuss today, such as organic crystals. And finally, not as much why we're doing the science, but we're also interested in developing a HPC-ready API for eventual open source deployment. And so what exactly am I going to present to you today? First, a brief introduction to the electron-phonon problem and single particle spectroscopy. I'll describe our method, which we call the Generalized Green function cluster expansion, GGCE for short. I'll show you a few selected results, which you can treat as benchmarks for the effectiveness of the method. And finally, I'll highlight the API and current and future usage of HPC. So what exactly is the electron-phonon system that we're considering? So basically, we have an infinite 1D lattice of sites in which the electron can live. And this electron can move around, it can hop from site to site, and it can create phonons. And a phonon can be thought of as a local quanta of energy. It really realistically corresponds to a lattice distortion. But for the sake of the model, you can think of it as a quanta of energy that is located on some site. And this electron can do two things. It is able to hop from site to site on its own, mediated by hopping strength T, which we'll discuss in a little bit. And it can also actually create phonons locally. So the electron actually couples to the lattice, and it's able to create these quanta of energy on the lattice sites. And of course, as is standard in condensed matter, we're going to describe our system by some Hamiltonian, and all this Hamiltonian does is it counts the energetic contributions for some state. And so for example, in the first term, this is the free electron term. All this does is these C operators basically count the number of electrons with momentum index K and assign them an energy E sub K, also, or epsilon sub K, also known as the dispersion. The second term does the same thing for the phonons. It simply counts the phonons that exist on the lattice and assigns it energy omega Q based on its momentum quantum number Q. And in this case, we're actually going to approximate omega as a constant, but in principle, the idea is the same. And finally, there's an interaction term, which actually describes a linear coupling. For those in the condensed matter community, you'll recognize B dagger minus Q plus BQ as a linear coupling in real space. But all these terms do is create and annihilate phonons. And what this does is it's able to actually measure the interaction between the electron and the phonons. And that strength is mediated by what's called the vertex term. And this coupling in red actually renders the model non-analytic. So you must use, in general, numerical methods to solve. All right. So what do I mean by single particle spectra? This quantity, this response function, which corresponds to these single particle spectra, actually has a very concrete physical meaning. The process begins when an electron is injected into an otherwise empty lattice. The electron is then allowed to propagate throughout this system, creating and annihilating phonons. It can take many different paths. This is just one of them that you see here. And finally, after eliminating all phonons, the electron is then removed from the lattice. And there are many ways the electron can do this. Like I said, this is just one path the electron can take. And on the left here, I highlight a few different ways the electron's actually able to move through the lattice. So you can imagine it hopping 20 times, right, first, and then creating some phonons and then annihilating them, or maybe it just creates a phonon and hops a little bit and then removes it. It can take any different number of paths. And in fact, we have a quantity that measures and actually counts up all the contributions of all these paths, and this is called the Green's function. Quantum mechanics actually assigns the weight to each of these possible paths. So actually looking at the system from the outside and trying to understand, right, which paths the electron is most likely to take, and smartly, right, sum the terms that you think are most contributing in G, because you can never calculate this exactly. That's essentially the job of the many-body physicist. And actually, each of these terms, right, each of these operators corresponds to one of these physical processes I just described. So in green here, the CK dagger actually is what's creating the electron or injecting the electron into the system. This e to the minus ITH, where H is an operator, is actually propagating the electron through the system in all different possible ways. And the CK term is actually annihilating the electron from the system. So this term is very interpretable in that sense. And this GK of T in the time domain, I failed to mention, right? This T is just time, is actually often much more convenient to understand in its frequency space. So omega is just the Fourier transformed right version of this with respect to T. And this object here is very important because it's actually experimentally measurable. In fact, the imaginary part of G is directly what is observed in angle resolved photoemission spectroscopy. And it's A that I'll be presenting to you today. Not to worry, if you know A, you actually can derive G. They're related by analyticity through Kramers-Kronig relations. So these terms are essentially equivalent. And when I talk about A today, I'm going to be mainly going to be, you can think of this as referring to G and connecting back to this discussion. So what actually is our methodology? I just got over, done telling you that you can't actually sum up all of these terms. It's in fact an infinite sum because there are an infinite number of ways for the electron to propagate on the lattice. And we're going to have to take some approximation to solve for G. And before going into our method, I'd like to highlight the sort of precursor method for what we developed, which is called the momentum average approximation, developed by Mona Bersu in 2006. And the crux of this method is that it leverages a physically motivated ansatz that phonons come in clouds. One of the reasons for this is that it is known that the ground state of a lot of these systems is called a polaron, which you can think of as a renormalized electron. It's an electron that moves through the lattice, kind of like an electron, but it's dragging along these lattice vibrations with it. And the approximation formally restricts the maximal cloud extent M and the total number of phonons allowed on the chain in real space. And so you can see here, this would be a M equals 3 because there are 3 contiguous sites occupied, right, by phonons. And in fact, actually, you don't need anything occupying in the middle. If the leftmost and rightmost sites are separated, right, by M indexes, right, that's satisfactory. There's no restriction on the position of the electron in these methods, aside from those that are imposed by the quantum mechanical formalism I just described. And this code is, this method is usually cheap enough that you can actually run it on your laptop and get really good results. And there have been many papers published using this method. However, there are lots of parameter regimes, such as the strong coupling limit or the very, very small phonon frequency limit, in which this method does not give converged results. And that's where our method comes in. What we do in the GGCE is we generalize the momentum average method to essentially a sliding scale for M and N. We allow the user to choose their own level of theory. And in principle, we can converge results with respect to M and N. It also seamlessly handles multi-phonon mode models. It also seamlessly handles finite temperature, which I don't have time to discuss today, but I'll go into a little detail in one of the results. It can be easily extended to more than one dimension, multi-carrier band and multi-carrier models. We're developing a user-friendly API for this. We have HPC-ready firepower at the ready. The scaling is not good on paper, but empirically it is tractable, and the user can always choose the M and N value that they want, sufficient for their own resources that are available. And finally, I just want to sort of cement in your heads kind of what I mean by solving this system. For every K, omega, M and N value, the task at hand is to actually solve a huge system of linear equations. So that's what we need these solvers for. So I'm going to quickly breeze through some example results to show you that our method works, and without getting too much into the physics. So for the Holstein, for example, for the Holstein coupling, which looks like this, where this is a local coupling where you're counting electrons, and creating and annihilating phonons on the same site. We're able to converge our results very easily. DMC is diagrammatic Monte Carlo. This is often referred to as a benchmarking method or a numerically exact method. And you can see that for various values of the dimensionless coupling, which is just related to the coupling you see here, alpha, we are able to get very good results, even for relatively small omega, which is quite difficult. And we're able to converge results for even smaller in what's called the extreme anti-adiabatic limit. So this is a numerically challenging task, which our method is able to sum up pretty effectively. Next, I'll talk about what's called a dual-phonon-mode model called Holstein+Peierls. So you can see on the left, you've got the same Holstein term as before. On the right, we have a different kind of coupling. This one is non-local. And in fact, this method is actually quite relevant to real materials. So this is why we're exploring this. On the left here, I have the momentum frequency resolved spectral function. And again, you're just gonna have to take my word for it. These results are converged. We discussed this more in our paper here, but we wanted to show essentially that we could do this. And I don't believe these results have ever been presented before. And finally, I'll present a few finite temperature results. So again, I'm not gonna go too much into the physics here, but what I want you to take away from this is that DMRG, density matrix renormalization group, this is actually also what is considered to be a numerically exact method. And our thermal GGCE, which I call GGCET, with some parameters m and n, converges to the DMRG result, which is very nice. We do this using a method called the thermal field double. Essentially, what this does is it maps a finite temperature n-phonon mode model onto a 0 temperature 2n-phonon mode model. And I'll go a little bit more into the scaling troubles in the next slide, and of course, how we're going to tackle them. And the ground state's no longer a polaron. And in fact, this is the polaron peak here, and there's a lower energy state corresponding to actually a polaron ejecting phonon quantum, which is very interesting. All right, so to summarize the results, we present a variety of results to demonstrate the scope of our method. So far, in all these results, I will call boilerplate HPC methods have been sufficient. The single model results, such as Holstein, that was the first thing I showed, scale like n choose m, so n balls in m bins, basically. And our primary workhorse for this has been actually Corey Haswell. And for some of the calculations, I believe it was the Holstein+Peierls one, we maxed out around a 200 node simulation for that. However, future problems will scale worse, and we're going to require massively parallel solvers to do this. And to be clear, each of the k omega points for the boilerplate HPC methods have not parallelized a single linear solver instance. And so, as I said, right, the single model results scale like n choose m. Single model results at finite temperature will scale like n choose 2m. And if you want to do dual phonon modes at 0 temperature, those also scale like n choose 2m. And if you want to do dual phonon mode models at finite temperature, your scaling is much worse. So to even have a shot at these problems, we're going to need a lot of resources. And our current implementation, which we're still testing, is PETC plus mumps using parallel sparse solvers. And each k omega point can now be massively parallel across many nodes. Finally, I want to highlight some of the API. So we wrote this to be very, very easy to use and hope to open source it in roughly a year or so. Models are constructed using just a few lines of code. The suite of serial executors, which call various backends like NumPy, Dense, with MKL, SciPy sparse solvers, are just a few lines of code as well. And finally, a big thanks to Stepan at UBC in the Bersu group, who developed the momentum average method. He wouldn't be able to do this without him. We've actually coded up a very simple API for wrapping PETC plus mumps. So it's essentially HPC ready out of the box. And so in summary, what we've done is we've generalized the momentum average family of methods to the numerically exact limit. We're ready to go with HPC, and we've used this method to probe some interesting physical results, which unfortunately I didn't have the time to discuss today, but I'm always happy to talk about it if anyone has questions. So thank you so much for listening to my talk. Big thanks to the CSGF coordinators for making our annual program review actually happen. To my coworkers, Dave, my advisor, John, my de facto advisor on this project, one of Dave's postdocs, Andy Millis at Columbia Physics, Mona Bersu at UBC Physics, and of course, Stepan at UBC Physics. And thank you for the institutional support, funding, and resources. DOE CSGF could have done this without you. Thank you. Columbia for providing me a home, and Nurse Corey for the resources. Thank you so much for listening. I'll now take any questions you may have.